Last time we ended the session talking about the double spending attack. So just to refresh your memory on this, we have two different people. We have a merchant and a customer. The customer is going to pay using Bitcoin. And the question is, when can the merchant be sure that they're really getting the money? So this was the case when we were talking about vending machines. So we said that the merchant just publishes their public key, their Bitcoin ID, and then the customer creates a transaction paying whatever fee they have to pay to the merchant, and the customer gives this transaction to the merchant. Now, of course, the merchant has to verify that this transaction is valid, and then the merchant also publishes the transaction and provides the item, but the problem we saw is that what happens if at the same time the customer creates a double spending transaction? So let's say this was the coin and the customer had created one transaction that was paying it to the merchant, and now they're creating another transaction paying it back to themselves, right? So then we saw that we have a situation here where there is a double spending attack basically, and one of these two transactions will end up in the consensus chain, at most one of them. And then we talked about this idea that the customer can actually bribe the miner. This is not necessary, but it will increase the chances of success for the attack, right? So as long as the miners put this second transaction into the consensus chain, the attack has been successful. Now, the solution that we saw at the end of last session was that, well, the merchant, in this case, we called him Bob, should wait for the transaction to be added to the blockchain. But how much time does that take? Well, it's going to take at least the time that is needed to add one block, which we said in Bitcoin, that's almost 10 minutes. So this is already going to take approximately 10 minutes. And so this means that you cannot have things like vending machines. Because when the payment is done, you have to wait for 10 minutes before you can give the item. And that's just not how vending machines work. That's just too slow. Okay? But is this enough? So let's say you're the merchant. A customer has bought something from you. They have given you a transaction. This transaction is announced on the network and it's now added on the blockchain. Are you sure that you're paid? Or is it still possible that something happens? Well, it's actually possible that the block that contains that particular transaction gets reverted, right? So this is like double spending, let's say by reverting blocks. Now, I don't know if my customer is a miner. It's possible that my customer has some mining power. We will talk about that. But generally speaking, let's say that I am Bob. I'm the seller here. I'm the merchant. And Alice is buying something. So Alice is buying something from Bob. And let's say Alice is paying Bob using transaction 1. Now, Bob does not trust Alice. Bob thinks that maybe Alice is going to do double spending. So maybe Alice is going to use the same coin in a different transaction that basically pays the money back to herself or pays the money back to another account that also belongs to Alice. Now, here's the problem. Alice can create a double spending transaction. So let's call this TX2. Which is double spending the same coin. Same coin. And now Bob is looking at the blockchain. He's hoping that transaction 1 ends up on the blockchain, right? So this is our blockchain. Let's say this is the end of the blockchain. There's something else going on there. And at some point, Bob sees that a miner is adding a block to the blockchain. And this block contains transaction 1, the transaction that was paying the money to Bob. Now, at this point, Bob can still not be completely 100% sure that this transaction is going to remain in the consensus chain. because it is possible that at some point there is a fork like this, and let's say transaction 2 is in this one. And then we had the rule that the longest chain is always the consensus chain. So it's possible that this one becomes longer, right? And if this happens, as we talked in the last session, this means that this block and all of the transactions in it are basically reverted. So no one cares about those transactions anymore. And that means that transaction 2 ended up being in the consensus. So Alice owns the money. Okay. Now, if you're Bob, what would you do? Well, mathematically speaking, you can never be 100% sure, right? Because no matter what, even if you have this transaction here and you have, let's say, 1 million blocks after it, it's technically still possible that someone creates a fork and that fork doesn't include your transaction and that fork becomes the longest chain at some point, right? But of course, that's not very probable. So what Bob would do in this case is very simple. He would just wait not only for this transaction to be added to the blockchain, but also for a bunch of blocks to be added after it. Okay, so let's say there is another block added here. Now, as soon as another block is added here, it's now less likely that this block gets reverted, right? Because in all likelihood, this is going to be the longest chain and no one is going to fork that deep. But if there is then another block added, then it becomes even less likely and so on. So each one of these blocks is usually called a confirmation. Okay. So a confirmation on my transaction is a block that is added after the block that contains my transaction. And basically we call it a confirmation because it makes it less likely that my transaction at some point gets reverted. Now, the rule of thumb that a lot of people use is to wait for 6 confirmations. By the way, some people also count the original block containing the transaction as a confirmation. So you wait for 6 confirmations. So now the idea is I'm going to wait until my transaction gets added to the blockchain. But when it gets added to the blockchain, I'm still afraid that maybe it gets forked out. So I'm going to wait until the chain containing my transaction gets much longer, until it has 6 confirmations in it. And at that point, I say now it's very unlikely that someone would find a longer chain, right? So based on this, how much time do I need? Well, I now need an hour, right? Because every one of the blocks is going to take 10 minutes to be mined. Almost, well, actually in Bitcoin, it actually takes 9.5 minutes, but let's say almost 10 minutes. So if I want to wait for 6 confirmations, I'm waiting for an hour, which basically now means every transaction takes 1 hour. So you don't have fast transactions. You cannot have something like a vending machine because, well, I mean, you can have a vending machine, but the seller must basically trust you. And if the seller doesn't want to trust the buyer, they have to wait for 1 hour until they're sure the transaction is done. Okay. Great. Now I want to talk about some other aspects of this whole blockchain protocol. One of the things I want to show you is pool mining. So suppose that you are a miner. Let's say Alice is a miner. But we just saw that the total hash power on the network is huge. So even if you're a miner, even if you have invested, let's say, $1 million buying hardware and so on, your chances of mining the next block are actually very low, right? So you're just, let's say you have bought some hardware, you've plugged it into the electricity, and it's just computing hashes. You hope that it finds a solution to the proof of work puzzle. but maybe, let's say on average, it finds a solution every 2 years or something, right? So let's say she has a small percentage of the total mining power. And now the problem is that it takes a very long time for her to find a block. So she has to basically do the mining for a long time, pay for electricity for a long time, and then just hope that maybe after a year, after 2 years, she finds one block. And we've seen that the block reward is actually huge. The block reward is almost 500,000. So when she finds the block, she gets a huge reward. Okay, so it takes a long time to find a block, but the rewards are huge. Now, if you're already rich, maybe you don't really care about this. Maybe you say, fine, I'm just going to do a long-term investment, and I'm going to only care about the expected returns. I'm just going to take the expected value of the amount of money that I'm going to make, and I say that's positive, so I'm going to do mining. But for most people, this is really not doable because they will go bankrupt before they mine their first block and before they get their first reward, right? So we need to somehow work on the distribution of the rewards so that it's not so unpredictable. Let's say Alice wants to have a steady income stream from her mining. So how can we do that? Well, the idea is to do pool mining. And basically, this means that a bunch of miners come together and they collaborate in the mining. They put their hash power together. And they say that we also share the rewards. Okay, so pretty much we're reinventing capitalism here. It's the idea of having a company. So this is what a mining pool is. In a mining pool, you have many collaborating miners. And let's say if I have n miners, each one of them has a different hash power. So let's say I have miners M1, M2 to Mn with hash power. And by hash power, I basically mean the number of hashes that they can compute in every second. Let's say the hash power of the first one is P1, the second miner has hash power P2, and so on. And the last miner has hash power P. So if they can somehow collaborate with each other, their hash power would be, of course, the sum of all of their hash powers, their total hash power. And then they should also divide the rewards. But of course, I want the rewards to be divided in proportion to the hash power that was actually contributed to the system, right? So the agreement is that we all mine together and divide the rewards. Okay. Now, several problems. The first problem is, what does it mean when we say we all mine together? Because we talked about this, we said that every block has some metadata, and that metadata includes the address of the miner who's going to get all the rewards from that block. So both the block reward and the transaction fees. Now, who's going to get those? I have n different miners here. Which one? So that one is kind of easy. I can say, well, we just choose someone as the manager, and then the manager gets the money. So this creates a little bit of the centralization, but let's say we don't care about this. So let's say we have a manager, and this manager has some public key with public key, let's say PK, and all of the miners agree to use the manager's public key when they're doing their mining. So they all mine together using PK. Now, why is this important? Because remember when I was solving the proof of work puzzle, my proof of work puzzle depended on the whole block. So I had to find the nonce such that the total hash of my block is small, right? But my block also included the public key of the miner, so the public key who's supposed to receive all the rewards. So if I'm using the mining pool's public key and I find a solution, I cannot steal it for myself, right? So this is the idea. Let's say I have this block. It has a bunch of transactions, right? And then at some point, I have the public key that was given to me by the manager. And now I'm doing proof of work on this. So I'm trying a bunch of different nonces. Okay, so I have this nonce here. I'm just trying random nonces, computing the hash of the block, checking if it solves the proof of work puzzle. Now, suppose that at some point I find a solution. So at some point I find a nonce such that the entire hash of this block, including this nonce, is less than or equal to the difficulty value that I had for my proof of work puzzle. Now, if I'm one of the miners and I find this kind of solution, I cannot just change this public key and put my own public key there, right? Because changing this public key would change the block, which means it would change the hash of the block, and then it would no longer be a valid solution to the proof of work puzzle. So if a miner is mining using the public key of the manager, using the public key of the pool, he cannot then steal the solution. But then the other question is, how do we actually prove that we are mining using the public key of the pool? So I have all these miners, I have n different miners, and they have to somehow prove that they're actually using the pool's public key for their mining. And they have to also prove how many hashes they're calculating in every second, right? Because we said that we want to divide the rewards based on the contributed hash power, right? And of course, another problem here is that, as usual, we don't trust anyone. So if I'm a miner, maybe I do half of my mining using the pool's public key, and I do the other half using my own public key. We somehow need a way to make sure how much each miner is actually contributing to mining using the pool's public key. And the solution here is actually, again, proof of work, but we're going to use a lower difficulty. Proof of work with lower difficulty. What does this mean? So suppose that the proof of work that you have to provide in order to actually add a block to the blockchain requires you to find a hash that has, let's say, 32 zeros at the beginning. Okay. So a valid proof of work, I'm just setting the value of this D basically. So let's say a valid proof of work solution, I'm assuming this, requires the hash of the block to be like this. I want a ton of zeros at the beginning. Let's say I want 32 zeros, and then something else. Okay. Now, this 32 is just a random number that I'm using here. It's arbitrary, it doesn't really matter. Now, if someone finds, if one of the miners in this pool finds a valid solution, of course they would publish it, and then the rewards will go to the pool manager, and everyone can see how much reward was found using this public key, so everyone knows how much they should ask from the pool manager, right? But the other question is, for the miners who didn't find a valid solution for proof of work, how much did they actually contribute? Now, for that, we say, okay, let's look at a simpler proof of work. So let's say I call this a partial solution. I say a partial solution is a block such that when I take its hash, instead of 32, it has maybe 20 zeros at the beginning. Okay, so a block B prime such that hash of B prime is something like this. It has a bunch of zeros. Now let's say 20 zeros, and then the rest of the hash. Now, if a miner finds a partial solution, they cannot use this to add a block to the blockchain, because the blockchain difficulty is this one. It's saying that you need 32 zeros at the beginning of your hash in order to add a new block. But they can use these partial solutions to prove to the other people in the same pool that I'm actually doing the mining using the public key of this pool, right? So you can have some other communication protocol outside of the Bitcoin protocol, where whenever you find a partial solution, you just publish this partial solution and everyone else in the pool sees that you found this partial solution. And then your contribution, your hash power, is basically proportional to the number of partial solutions that you found, right? And that makes sense, because if you're calculating more hashes, you're going to find more partial solutions. So when a complete valid solution is found and when a new block is added, the manager receives all the rewards, but then the manager will divide the rewards among all of the miners in proportion to the number of partial solutions that they have submitted. Okay. And if the miners have a way of communicating with each other, let's say, I don't know, we have a bulletin board or something, everyone can see these, everyone can verify that there is no cheating. Okay. So this is how we do pool mining. Now, a problem that I want to consider here, which is actually mainly due to this pool mining, is the problem of centralization. So remember, at the very beginning of this course, I was trying to give you different definitions of decentralization. And one of the definitions that I gave you was this idea that everyone on the network has exactly the same permissions as everyone else. And that's what we have achieved in Bitcoin right now. So anyone on the network can decide if they want to be a miner or not. We talked about this. You can just be a normal node, not take part in mining at all. Or you can invest as much as you want into the mining equipment and actually do mining. But here's the problem. In the Bitcoin protocol, we're assuming that the majority of the miners are honest. And let me just write this down. This is Bitcoin's, let's say, main security assumption. It's assuming that a majority, well, we can't really know how many miners we have, because of course, everyone can create as many accounts as they want, and that includes the miners. So if I'm a miner, I can create many different public keys and mine using many different public keys. So it doesn't make sense to count the miners, but we can always talk about their hash power. So the assumption is that a majority of the hash power on the network is controlled by honest miners. Okay. So several points here. First of all, what do I mean when I say honest? I say someone is honest if they're following the protocol, right? So remember, we talked about the protocol, and especially we talked about this really important part of the Bitcoin protocol, which says that you always extend the longest chain, right? I don't have a way of actually enforcing that. If a miner decides to extend some other chain that is not the longest chain, there is nothing that can stop them. But that's a dishonest action, right? And for our security, we're just going to assume that a majority of the hash power is honest. So a majority of the hash power is going to follow the protocol. And by majority, of course, I mean more than 50%. And again, by honest, I mean follows the protocol. Now, what happens if we don't have this kind of situation? What happens if a majority is dishonest? So imagine that I have an attacker, and this attacker has somehow gained more than 50% of the total hash power. What can the attacker do? Okay. So what can you do with more than 50% of the hash power? Well, such an attacker can basically create as many forks as he likes, right? So let's say this is my blockchain again. And let's say this was the last block that was mined. And let's say that the attacker doesn't like this last block. The attacker can simply fork it like this. Can create a new block here. And now we have a fork. But let's say the honest miners add another block here. Now, if the attacker were honest, he would have to extend this one because this is the longest chain. But of course, we're talking about an attacker. He's not honest. So he's going to try to extend this one. But he has more than 50% of the hash power. So honest miners are trying to extend this chain. The attacker is trying to extend this one. He has more hash power. Eventually, his chain is going to get longer. Maybe this goes on for a number of blocks. But at some point, the attacker chain is getting longer. And now remember, the rest of the miners are honest. So as soon as the attacker chain gets longer, because they follow the protocol, they always try to extend the longest chain. So they just switch to the attacker's chain. And so this means that all of these blocks are forked out. They're all reverted. That's what you can do if you have more than 50% of the hash power. And also, you can do this not only with the last block, you can do forks like this as deep as you like. So if you don't like the last 10 blocks or the last 1,000 blocks or whatever, you can just fork from any point that you like, create a new chain, keep mining on your own chain until your chain becomes longer than the current consensus chain, than the honest consensus chain. And then all the honest parties will also switch to your chain. So basically, if you have more than 50% of the hash power, you can pretty much rewrite the entire history of the blockchain, right? So you can create arbitrarily deep forks and change the history, basically. Okay. But remember, the most important problem we had and the whole reason we created a blockchain was the double spending problem. But if you can rewrite the history, you can also double spend, right? So let's go back to this scenario here, this one. So Alice is buying something from Bob. And let's just assume that Alice has more than 50% of the hash power. So she creates a transaction. So let's say Alice creates transaction 1, paying Bob. Okay. And this is my blockchain. Bob, let's say, publishes this transaction, and at some point, Bob's transaction is added to one of the blocks. And Bob is also very cautious. He's going to wait for 6 confirmations. Okay, so this block is added here, and then after it, I have 5 more blocks. At this point, Bob is completely sure that he's getting paid. So he gives the item to Alice. But remember, we're assuming that Alice has more than 50% of the hash power. So now she creates another transaction, which is basically double spending the same coin as in transaction 1 and is paying it to herself. So Alice creates, let's say, transaction 2, which double spends the same coin that was spent in transaction 1. And let's say pays it to herself. Now, the problem is that transaction 1 is already on the blockchain. So Alice is going to create a dishonest chain, a fork like this. So a new block that says my previous block is this one. And she's going to put transaction 2 in that block. Okay, this is a fork. But right now, it's not the consensus chain because the honest chain is longer. But again, remember, Alice has more than 50% of the hash power. So she can just continue adding blocks to the end of her own block and keep doing this until it gets longer than the honest chain. Maybe while she's doing this, people in the honest chain are also adding something. But it doesn't matter. At some point, her chain is going to get longer because she has more than 50% of the hash power. And again, as soon as her chain gets longer, everyone is going to adopt the longest chain. So this whole part here, this honest chain, is basically reverted. And now at this point, we see that transaction 2 is in the consensus chain, which means that double spending was successful. So if you have more than 50% of the hash power, you can rewrite the history, you can double spend, you can pretty much do whatever you want. Okay? So Bitcoin's security really depends on this assumption that more than half of the hash power is in the hands of honest miners. And again, honest means someone who follows the protocol, someone who always extends the longest chain. Now, here's the thing. Another way of looking at decentralization, instead of saying that it's decentralized if everyone has the same permissions, is to say it's decentralized if any kind of attack needs a lot of people, right? So for example, if I have something like this, if I have a majority attack like this, how many different people or entities does it take in order to be able to do an attack like this? Now, in the case where we had a central bank, we saw that the central bank itself can just do a bunch of attacks, right? So that was the most centralized case. But now the question is, what about Bitcoin? Suppose that I've made a transaction on Bitcoin, and suppose that some people want to revert my transaction. How many people does it take? Okay, so who has the power here? Or something else. Suppose that you're a powerful government. Let's say you're not happy about certain transactions on Bitcoin, and you want to stop those transactions. Can you do it? Well, technically, if you have enough money to buy more than 50% of the hash power, then you can do it, right? And actually, it doesn't take that much money. It would take maybe having more than 50% of the hash power these days would cost something like $7 billion. So if you invest $7 billion and you buy half of the hash power, you can pretty much do whatever the central bank could do in the centralized system, right? But there is a bigger problem. Remember, we talked about mining pools. We said that people actually pool their hash powers together, and then there is a manager, and they use the manager's public key to do all the mining. But it's actually usually giving even more power to the manager. Usually the manager says, this is the block that we want to mine. And everyone in the pool tries to find nonsense proof of work solutions for that particular block that was formed by the manager. So these managers actually have control over the entirety of the hash power of their pool. Now, how many pools does it take to reach more than 50% of the total hash power? So here's the current distribution. This shows how much hash power each pool has, and it takes 2 right now. So if the managers of these 2 pools collaborate with each other, they have more than 50% of the total hash power. And so unfortunately, Bitcoin is not decentralized at all. It's like literally like this. These 2 can rewrite the entire history. Okay. Now, but an argument you can have here is that these people have invested a lot into buying the hardware or creating the mining pool and so on, and they're making a lot of money from mining. And the money that they're making is denominated in Bitcoins. So they would not want to do an attack. Because if they do an attack, if they try to revert, let's say, a large portion of the blockchain, if they revert, let's say, more than 6 blocks, then people will lose, again, this part is economics, it's not really computer science. People will lose their confidence in Bitcoin, the price of Bitcoin will drop, and these miners will also lose money. So there is some sort of a hand-wavy argument, not really a mathematical argument, but like maybe a psychological argument, that these people are unlikely to do an attack. But the important point is that they can. So again, don't buy Bitcoin. Now, the other point here is, let's say you're a government. And let's say you want to blacklist some particular transactions. Okay. You can just go to these 2 people, the managers of these 2 pools, and you can threaten them. You can say, you censor these transactions or else there will be some legal consequences for you. Again, the whole point of decentralization was that there should be no central authority that can control anything, but there is a central authority here. Well, these 2 big mining pools. And actually, there was a time in 2014 when there was literally 1 mining pool that had more than 50% of the total hash power. So if you think governments don't have any control over Bitcoin, they actually do. Okay. Now, what else? It's actually kind of even worse and more depressing than that. So let me run another scenario by you. Let's say that you're a small miner and you're not taking part in any of these mining pools. You've just invested in your own hardware. You're happy with finding 1 block every 2 years, right? So you have done your investments. You've used a lot of electricity. Let's say after 2 years, you get lucky. You find a new block, okay? So this is, again, I'm always drawing the blockchain in this course. So let's say this is the blockchain. And after 2 years, you're lucky and you have added your block. This is the block of a small miner. Okay. It's a block that was mined by someone that no one else knows about. Okay. Now let's say that at the same time as you, or at approximately the same time, one of the big miners also finds a block. Okay. So at the same time, there is a block here by one of the big miners. Let's say by this one. Okay. Now, remember, the Bitcoin protocol says that honest miners should just follow the longest chain. And in this case, there is no longest chain. There are actually 2 different longest chains. So the miners get to choose which one to follow, right? And the idea, the original idea was that, well, they will choose randomly and you will still have a 50% chance of getting your rewards. right? So either this one will end up being the consensus chain or this one. In any case, if you're lucky and you become the consensus chain, you also get the roots. But in practice, this big miner owns a lot of the mining power, right? So what is the percentage? Yeah, so the biggest mining pool owns almost 32% of the mining power. So they're, of course, going to only try to extend their own block because they want to make the most money. And extending their own block will give them the transaction fees in this block and also the block reward. So they're going to try to extend this one. But it's even worse than that. All the other miners also know this, right? So you're not just competing with the biggest miner, but like all these other miners, they also know that this was a block that was added by a big miner. So it's actually risky for them to try to extend your block, because if they try to extend your block, since a big miner is working on this one, it's actually likely that another block gets added here at the same time, right? And again, remember, the miners are only caring about their own payoff, their own income. So it's risky to extend the block that was created by a small miner. So not only the big miner is going to extend their own block, all the other miners are also going to extend the block of the big miner, right? So in practice, whenever this happens, the big miner wins. And yeah, so this is going to be the consensus chain at the end of the day. And because of this, you shouldn't be a small miner. You should just always join a mining pool if you want to do mining. Okay. But this also shows another problem. Suppose that the big miner wants to censor some transactions. So let's say I'm doing some transaction, and for some reason, the top miner or the top pool doesn't like me, doesn't want to include my transactions. And additionally, let's say that the top pool announces to everyone on the network that if you include any of Amir's transactions in your block, I'm not going to extend your block. Okay. Now, this can happen for a variety of reasons. Maybe they really hate me, but maybe also there is something illegal in that transaction, and I don't know, I mean, they have USA in their name, so maybe the US government has some control over them, and they're saying, don't do these transactions. So maybe they legally cannot extend blocks that contain some particular transaction. In that case, the effect is very similar. So let's say that, again, I have my blockchain, and let's say that I've made a transaction, and it's a transaction that one of the big miners does not like. But someone else has mined my transaction and put it here, right? Now, if the big miner has announced to everyone, and let's say by big, I mean someone who has like 20% of the hash power. If the big miner has announced to everyone that they're not going to extend this, it means that the big miner is trying to fork it. Well, first of all, there's a good probability that they succeed. And if they succeed, then we're back into this situation and everyone is going to extend the big miner's block. But even if they don't succeed, other people would still be afraid of extending this block. Because 20% of the hash power on the network is saying that if you extend this, I'm not going to be honest. I'm not going to continue extending your block. And again, remember, as a miner, you want to maximize your own revenue. You want to maximize the probability that your block ends up in the consensus chain so that you get the block reward. So in this case, actually, all the other miners have an incentive to just try to fork it here. So even though no one is malicious, even though maybe only the big miner is malicious, everyone else is basically bullied into doing what the big miner wants. Now, this one didn't really happen yet, but it can happen. But this one happens all the time. So that's why if you look at these big mining pools, and if you look at the summary of, I don't know, last how many blocks, this is probably the last 300 or 400 blocks. none of them are added by unknown miners. All the blocks are added by one of these big mining pools. Basically, no one else is doing mining. These are the only players. And unfortunately, 2 of them have more than 50% of the hash power. Okay. Now I'm going to go to another topic, and I'm going to let you just think about what happened here, and hopefully you agree that you shouldn't buy Bitcoin. But I made a simplification when I was talking about Bitcoin transactions, and this is a common thing in this course. So I always lie to you first. I give you a simplified version, and then later on I come back in later sessions and say, well, actually there is more detail here. So one of the things that I said was that every transaction has a bunch of inputs and it also has a bunch of outputs. And I said that every output has 2 things. It has a value basically and a recipient, right? So it has a value and the public key of the recipient. Well, actually, it's a little bit subtler than this. It's not that you just give the public key of the recipient, but you can actually say what are the conditions in order to access this money. Okay, so it's actually not just value and public key, it's value and conditions to spend the coin. Okay, and we have a programming language. Actually, there is a Bitcoin scripting language that you can use to write these conditions. So these conditions are basically programs or scripts. Okay, so every time that you have an output from one of your transactions, you have a script. And this script is basically a program. It takes some parameters. If it returns true, you can spend the money. If it returns false, you cannot spend the money. Now, normally this program is just checking signatures. It's just saying, hey, I need a signature from this particular public key, which is what we were doing until this point. That's the simplification. But actually, the program can ask for more complicated things. And we will see some examples of this. So similarly, as I said before, every input is an output of a previous transaction. So that previous transaction has given the conditions for spending this output. And then this input should give the parameters. It should, let's say, if the conditions are checking a signature, then the parameter that I have to give is the signature itself, right? So that when I pass these parameters to those conditions, it returns true, and then I can spend the money. Okay? Now, let me give you one example of this. By the way, the Bitcoin scripting language is very limited. You can read about it on Wikipedia, but we're not really going to focus on the Bitcoin scripting language in this course because we have better cryptocurrencies with better programming languages. But just to give you an example of how a Bitcoin script can work, let's say we have 3 people, Alice, Bob, and Carol, and they want to create a joint account. And we want to say that you can withdraw from this account if a majority of the people agree. Okay, so I can create a transaction like this. I can create a transaction that has a bunch of inputs. I don't really care where the money is coming from here. And then let's say it has an output. And the output, of course, has some amount, let's say whatever, 100 Bitcoins. And then it also has a script. But my script, instead of saying that you require 1 signature from a particular person to spend this money, can say that it requires 2 signatures among, let's say, Alice, Bob, and Carol. And again, I'm writing names here, but they're actually public keys. So I can have a script that hard codes 3 public keys and says, if you want to spend this coin, you need to give me 2 signatures as parameters that are signatures of 2 of these 3 people. And so now none of them on their own can spend this money in any transaction. But if at some point you create a transaction that has the consent of 2 of the 3 people, which is again based on signatures, then it can spend this money.